Yeah, so last time, let's have a quick review on the last lesson that we discussed about the inferential statistics. So we talked about what is the point estimation and testing hypothesis, right? What is the purpose, and explained about the inferential process. Um, that is from population, we draw samples and sample statistics, uh, and finally estimates and do the tests. We also talk. We didn't talk about the test at that moment because test gonna be the next section. Whole section is about the hypothesis testing. Later on, we will talk more about this. I think in after couple of lessons, we will talk about hypothesis testing. We also talked in details about the estimators and about sampling distribution, then population characteristics, where we took an example and measured, right? So these are the some estimate. So before that, these are the some estimators like the population parameters and sample statistics, right? And mu and x bar is the corresponding sample statistics for the parameter of mu of a population. Similarly, small s square and capital S square for sigma square, rho for the proportion of a single population. Rho is population parameter, and phi that is phi hat is like sample statistics. And difference in mean of two populations. We will also do some examples about the difference of mean of two sections today. So this we will talk more about this a little bit today. All right. So then the population characteristics, where we took example measured summary measures of sample mean. Uh, we took the distribution, and from that distribution, we took the distribution of sample means distribution, right? Where we talked about population and sampling distribution. We ended the last lesson with three properties of sampling distribution of mean. That is unbiasedness, which means that x bar equals to mu, or x bar tends to mu, mean of sampling distribution equals to population mean. We talked about efficiency. So these are the properties of sampling distribution. That the mean is the best um, and the closer to the population mean than any other unbiased estimator. And third one is consistency. As sample size increases, variation of sample means from population decreases, right? Population decreases. So that's about um, the thing which we have covered already in last lesson, in last Thursday, right? So today we will continue the same series of topics, and we will see that how to prove that unbiasedness, as we have discussed that expected value of x bar is unbiased. What does that mean? So let me take you to the whiteboard so that you can see. Now, what does that mean about the unbiasedness, right? So if you see the board clearly, just let me know that you're not facing any problem. Now, we have discussed x bar. You can see the whiteboard clearly, right? So what is X bar? X bar is unbiased. That's the first property, right? Estimator of population parameter. Now we have to see that if it's really true or not. So what we claim is that expected value of X bar equal to mu. Is that right? Yes, this is right. So we already know that X bar is sum of X upon N, right? You can say I equal to 1 to N. Now, if I open this summation here, if I open this summation here, then what we get? We get expected value of X bar is going to be expected value of X1 plus X2 plus X3, so on, Xn upon N, right? I just opened this summation. We have so many X, right? We have a number of observations. Now, every number of observation has some disturbance. And as we know, the property of expectation. What is the property of expectation? You can tell me the property of expectation. That we take the constant outside, right? When we put the expectation here, we just take the constant outside. So far, this is the n. So we take the constant outside, and it will lead us 1 upon n outside, and then expectation of x1 plus x2 plus so on xn. Is that right? We have second equation, this one. Now we apply expectation on all the variables. And as we know that expectation of x, what do we know? The expectation of x is mu. So what will be the expectation of x1? Because every variable has a disturbance term of a mu. So there it will be x1. So we can say that expected value of I equals to mu. So expected x1, x2, x3, all of them, they have some disturbance term, right? So can I write this one as 1 upon n mu plus so on mu, n times mu, right? I can easily write that. And this will lead me to this conclusion that expected value of x bar, the mean, is n mu upon mu upon n, right? This n, and that's n times mu. This one is n times mu, and that's n. This one cancel me, and it will give me same result. So hence we have proved that the sample mean x bar is an unbiased estimator population parameter because its estimation becomes equal to the population parameter. So that's a really important parameter property here, which we're going to use further as well. Population x bar is an unbiased estimator population parameter. Do you understand? So similarly, second thing is we are proving. Is it clear? Is this clear? That how the expected value of x bar equals to mu. Now, similarly, let's talk about this. Now, it's really simple. We talked about that the mean variance is also an unbiased estimator of sigma square, right? But which one? We are proving that the small s, we already talked last time in the last lesson, the small scale that that is the formula of small scale, and we know what is the formula of small scale. It's given as sum of x minus x bar square upon n, right? Minus 1. That's the small s square. Whereas the big S square, it's sum of x minus x bar square upon n. Well, let me take two things parallelly. Now it's really easy. We know this formula. So here, this sample, what we want to know is that variance. I'm writing here. I think you can see this. Variance. If you can't see properly, just let me know at once, okay? Now, what we say that variance is an unbiased. So first we talked about that the x bar is an unbiased estimator of the population parameter mu, right? The variance is an unbiased estimator of the population variance. Of a population variance. It exactly equals to sigma square. Now, which variance? Right? We are talking about the small s square. We consider big S square that it won't be exactly equal to the sigma square. So let's so in other sense, what I need to do, I need to prove that small s square equal to sigma square. On the other side, we will also see that the expected value of big square is not equal to sigma square. Right? So if this holds, it means the small s square, the variance is an unbiased estimate of the population variance sigma square. I mean, talking about the sample variance. And this term here, it doesn't. Let's open this one first, one by one. Again, constant will come out when we take expectation. Just apply expectation on this. Small s square equal to what we can do. We can solve like sum of x minus x bar square upon n minus 1. Similarly, steps you can take from further big S square, right? Again, this is the constant 1 upon n minus 1, so it will come outside. So I will just write it outside, and I can write this one as 1 upon n minus 1 as an expected of inside is sum of x minus x bar here, right? So now this apply that simple formula which you have learned in high school mathematics, that a minus b whole square equal to a square plus b square minus 2ab, right? So if I open that one, we go to this formula. So I will get summation x square plus x bar square minus 2 x times x bar, right? Now I know about this x, or when I apply x here, what will I get? Wait. Open this formula and then apply the summation inside. This is x bar is constant, so we have learned that when we apply summation to a constant, what do we get? We get n times of that constant, right? So if I apply summation inside, so I will get sum of x square plus n x bar square minus 2 sum of x bar. That I will get, right? I hope you can see it clearly. If you can't, just let me know. Okay, let me write in a big. So if I just I think now it's clear. Bar, right. So same thing you apply here. You are doing it in parallel. I'm doing that because it's the same steps. The difference is that instead of n minus 1, there is n. So what you would get now here, we know sum of x is what? Nx bar. Because we know that x bar is equal to sum of x upon n. So you just change the places and you will get this one. If I put this one here, so it will be 2 expectation of sum of x here plus nx bar here minus 2 here you put this nx bar, so nx bar and x bar, so it will be 2 nx bar here. That's what we get, and 1 upon n minus 1 expected value of sum of x here minus nx bar here. That's what we get. Now I'm just removing the rest, it's erasing the rest of the steps because to get a place, and I will continue from here. Right? So just to get the space here, so I can write this one. So I solved here, then I get to this one, 1 upon n minus 1 expected value of sum of x here minus nx bar. Right? This you got. Now, apply the expectation here. Right? We have numerical value, so we just apply the expectation here. What we will get, the equation will be 1 upon n minus 1 expected value, just apply this expectation here inside, so we get sum of expected value of x here minus n expected value of x bar here. Now we need to find out the value of this one and this one. As we know that the variance, what is the variance? You tell me. Expected value of x here minus expected value of x whole square, right? Can I write like this? Variance of x is sigma square, right? This is expected value of x square minus, can I replace mu here? So this can be mu square. Can I write like this? I repeat. Variance of x right, this one, so I can write here sigma square minus mu. Can I write this as mu, right? And square. Now from here you can get 2 and square, what? Equal to sigma square plus mu square. Can you get this from here? You can get it, right? Easily. This value right here, right instead of this value, just put here. So what you will get? You will get here sigma square plus mu square. Same thing you apply here. If you apply here, what will you get? What will be the variance of x bar? This one? x bar square and x bar square. Now, as before we talked about the expected value of xi is mu, right? So x1 is also mu, x2 is also mu. So x bar will also be mu, right? There will be disturbance. But here, what will be the variance of x bar? It will be sigma x bar. Yeah, sigma square x bar. And we also know that sigma square x bar equal to sigma square upon n. That's we know. Because there's a sample mean is equal to the variance upon n. Right? Or you can say sigma x bar equal to sigma upon under root n. We have talked about this thing in last. We just put the same thing here. But instead of sigma square, it will be sigma x bar, which is what? Which is sigma upon sigma square upon n. So I can write like this. Sigma square upon n plus 1. Now replace the same values here. Is it clear? Just put these values in this equation. What you will get? You will get 1 upon n minus 1 summation mu square plus sigma square, right? Minus n. And it's as it is. And what this value was? Mu square plus sigma square upon n. Now you know how did I get these values instead of this, right? Just simplify it and you will get 1 upon n minus 1, and when you put the summation inside, it will give you n mu square plus n sigma square minus n mu square minus sigma square. Right? So this will be cancelled out. Sigma square will be taken as a common. So 1 upon n minus 1 times sigma square n minus 1. This will be cancelled out equal to sigma square. Right? So here we talked about this thing. We have proved this thing just right here. Is it clear to you guys? Simple, not that much difficult. Just a bit of calculation and you can prove the variance. Say if sample variance is an unbiased estimator of a population variance. Now, what is the unbiased factor? If we consider this one, here we have n. Now, look. So let me raise this and let me tell you the interpretation of these things. It's very simple. We have, in this one, we have proved it. Now, so what does that mean? Equal to sigma square, right? And before step was? If we consider the same one, so whole population will be the same, but at the end, it will be 1 upon n. And then we get sigma square upon n minus 1. Right? I'm talking about S. In that case, we had n minus 1. Now that gave me the sigma square. In this case, n minus 1 upon n. Right? Sigma square, which is not equal to sigma square. Why? Because this one, n minus 1 upon 1. This is the unbiased, this is the biased factor. Right? If this becomes 1, this is equal. So because of this biased factor, it's not an unbiased estimator. Here we don't have a biased factor. Right? Here we cancel out n minus 1 and n minus 1. That's why we consider the small x here as The small variance is the unbiased estimator of a population variance. So these are the two things about unbiasedness. Hope that you have understood uh, that here this is the bias factor on the basis of which we say that x k is not equal to sigma square. And here we say small h square equal to sigma square. So hopefully that you are clear on this topic, how we can show that mean, x sample mean, x bar, and samples variance are the unbiased estimator of population parameters, and S capital S is not. So is it clear? Guys, is it clear? Perfect. So I hope that it's really clear to all of you. It's not that difficult. You just need to understand that what do we mean by the unbiased estimator. Now, if we move next, and let's go back to the slide on here. So exactly these things we have done. I have done in details because this is just to save time. We reach to the conclusion of this one, right? And the same thing we talked about the sigma scale. So now there must be no ambiguity in understanding this one. Now let's talk about the central limit. This is a really, really important one. Right? So let's understood that a very key and important theorem. That is central limit theorem. What does it say? As we learned in the previous lesson, that we started with the uniform distribution, right? That is actual population. So I will also try to open the, let me also, if you can see the video as well, let me do it on the screen. Okay, let me do it on the screen. Which one ever is like convenient to you guys. Okay, so as we have learned that the uniform distribution can be, that is actual population, right? In last lesson, we talked about an example where we took the distribution of a population and it was a uniform distribution, right? And when and from that we collected different samples, and then with those samples, we drew the means. If I show you in last lesson, just like this one. Right, so we took samples, and from that samples, we have done the distribution of the sample means in last lesson, and then we draw the distribution. So before the distribution was, that was the population distribution, it was a uniform, and then we got the sampling distribution as a symmetrical distribution. This is called normal distribution, right? If you remember, if you recalled it from the last lesson. Now the same thing we're gonna do here. Now you know what is called normal distribution. So actually the central limit theorem states, now listen carefully. So this one, central limit theorem, you can also call it CLT. It states that the same thing. If we have n random variables, which we draw from a population, right? N random variable, which we draw from the population, And the population mean distribution will always be according to the central limit theorem. So central limit theorem says that as the sample size n increases, no matter what is the distribution will be. It's a uniform distribution, it's an exponential distribution, it can be any form of distribution. As the sample size n increases, it becomes a normal distribution. And you know the parameter of a normal distribution. The parameter of the exponential, uniform, and other distributions may be different, can be different. But normal distribution, the parameter mu is 0 and variance is 1. Sigma square is 1. So I repeat, what the central limit states, as the sample size n increases, any distribution, it becomes normal distribution, right? Just it's the same thing when we learned the previous example. In our previous example, the population distribution was uniform, and when we increase the n, the sample mean, it becomes normal distribution, right? So we can say that if, now let's talk about these things. If x1 up to xn is a random sample of size n, which is taken from a population either finite or infinite, with mean mu and finite variance sigma square, right? Because sigma square can be greater than 0 until the infinity, which is defined. Finite here means defined. And if x bar sample is the sample mean, then this limiting the central term is there. Now, here is an interesting point. If you recall, let me also share the video. If you recall, we have we have studied the z-score. What is z-score? Simple. That is z equal to x bar minus mu upon sigma here. We see, according to the central limit theorem, this is really important. That's the difference. X bar minus mu upon sigma under root n. What that's the difference between these two z-scores? Here we consider z upon sigma upon under root n, and here we just use the sigma. What does that mean? What does that infer? This we know. We call it what? We call it standardized, standard, a normal distribution, right? That's what we call standard normal distribution variable. And we interpret as a number of, how do we interpret z? Because it's a deviation, right? So we'd say that the number of standard deviation, what will be the standard size deviation from the mean? Standard deviation, your particular value, the particular value which we are studying, is lying away from the population. Right? So that's how we interpret this z-score. Whatever the value will be. If it's 1.2, then we say it's 1.2 standard deviation. If you remember, we talked about this. Mu plus minus sigma. So what is the area? 66.8%, right? Remember? And then plus minus 2 sigma, it was 95%. And then plus minus 3 sigma, it was 99.7%. So that's the same thing. We talked about this. So just put in your mind that whatever the z is, we interpret z as a number of standard deviation that the particular value is lying away from the population mean, right? Now, so that was regarding overall population, this one. Now we took this z regarding the sample. You see, understand the difference? Similarly, as we consider the mean, sample mean, as a variable, right? Here we were using x as a variable, so here you are using sample mean as a variable. And we know that according to the sampling distribution of the mean, what do we know? So this you understand. So I'm just gonna remove this one. So we already know that according to the sampling distribution of the mean. This is very important, mean. One thing, mu x bar equals to mu. Whereas, second thing, sigma in term of x bar is biased. That is, sigma x bar is not equal to sigma, it's equal to sigma upon under root n. Remember this thing from the last lesson? So this is biased. It's not unbiased. Unbiased, it would be equal to sigma. So over here, what will be the z-score? So the z-score, this applies, both of these. These apply that the z-score will be x bar minus mu x bar upon sigma x bar. This is going to be the z-score of the mean distribution of the sampling distribution of the mean, right? So here we will have sample mean and sample sigma variance, standard deviation, right? So it will lead us to what? This thing, x bar minus, if we apply this the same thing, x bar minus mu. Instead of mu x bar, I just put mu, and upon sigma over root over by under root n. So in central limit theorem, it states us this way. So as n tends to infinity, any distribution according to central limit theorem becomes a normal distribution. Do you understand? Is it clear? Is it clear to you? Do you understand that what is the difference between z-score when we are talking about x bar minus mu upon sigma, and when we are talking about this? So here we say z is a number of standard deviation, the particular value is lying away from the population. Here the z will be what? If we explain it, it will be the particular value. Z is a number of standard deviation of particular value is lying away from the sample, not from the population. So that's the that's for the overall population. This is the z-score. This is for the sample we have selected from the population z-score. Is it understood? Means is it clear? Let me know if you have any questions so far. Hmm? Is it clear, guys? If it's clear, we can proceed. Okay, perfect. Okay, good. So it's clear to only two of you, right? The rest of the class, what do you think? Now, okay, so let me share the screen again. So now, this you understand that from where we get this one, standardized normal distribution. Let's do an example. Yeah, so if we do an example, now here we have a uniform distribution where we have the function of x is given as this one. It's a uniform distribution. It's already told. So in continuous random variable, the uniform distribution formula will be, what is the uniform distribution formula? That is simple. It's so in continuous random variable, that's a continuous variable. The uniform distribution function will be f of x is 1 upon b minus a. Right? So when we talk about this, this is a, this is b, so b minus a is the function of, this is the area we are interested in, right? If you remember the very, like, I think 2 lessons before, we talked about this, where a is less than x is less than b. X lies between this area, this range. So that's in the continuous random variable, we have this uniform distribution. So this is probability. Here the probability is given half if a is 4 and b is 6. We also know that the distribution of n is 40, it's given, n is 40, probability is given half. Now we have to find out the distribution of a sample mean. How to do that? So if x probability distribution is uniform and its mean is, what will be the mean? All right, what we have to find out? We have to find out the distribution of sample mean. That's what we need to find out. In this case, we already know that the distribution, that mean is b plus a by 2, and variance is, that's a formula, b minus a square upon 12. So that's the formula for mean and variance in continuous random variable of a uniform distribution, right? So we're gonna go for the same thing here. So to get the mu, we have this one, 5. Now we know that by central limit theorem, x bar is a normal distributed. So now we can have a mu equal to b plus a by 2 and put the value, corresponding values in here as 5, and we also get the variance and put the corresponding values here, and it will give us 1 by 20, right? So now here you can also take the for sigma, you can of x bar, it will be under root of 1 by 120, whatever the value will be. So put this value, it's under root, right, of this one. Now if we draw the graph, we will see this was the uniform. This was the uniform distribution from 0 to 5. Now when we convert and see the mean, sampling distribution of mean, we got this one. So we have the mu 5 in the middle, and then x bar, it's really low, because this, you're gonna calculate the value, so it will be 0.000 something. So it's between this range, will be here. So you just put the values here, the distribution of x and x for x bar, it will be this one, right? So that's how we go for this one. Now we know the sampling from the normal distribution. So let's, although it's a normal distribution, but when we will be doing the sampling distribution, again our mean mu x bar, it should be equal to mu, and sigma x bar equal to sigma upon our under root n. So let's talk more about this after taking a break. At the moment we're gonna take like 10 minutes break, and then we can come back. Okay.